For the third Pythagorean identity for our hyperbolic function, we have here the square of the hyperbolic function of cotangent z minus 1 is equal to the square of the hyperbolic function of cosecant z. By the way, we have the similar perspective. We talk about a certain angle in real numbers, but it's not actually minus. As a Pythagorean identity for this, the square of cotangent theta plus 1, or 1 plus the other way around, is equivalent to the square of cosecant theta. Okay? Or, if we're going to remember, we're going to review for trigonometric functions for complex numbers, we're also able to understand that the square of a cotangent z, okay, as a complex number, plus 1 is still equivalent to the square of your cosecant, sorry, it's not theta, cosecant z. Now, these two already established the angles in real numbers, and this time complex numbers z. But for hyperbolic functions for complex numbers, it's actually minus this one here. And that's what we're going to show for this specific video, because we would like to prove this identity. Before we start with our proof, let's try to remember what is the equivalent form for the hyperbolic function of cotangent z. It's actually the reciprocal of your tangent, hyperbolic function of tangent z. It's actually equivalent to e to the power of z plus e to the power of negative z over e to the power of z minus e to the power of negative z. As for your cosecant, specifically the hyperbolic function for cosecant z, it's the reciprocal for your sine. So it's actually equivalent to 2 over e to the power of z minus e to the power of negative z. But since our task is to show that the square of that minus 1 is equal to the square of this, so our target is actually the square of cosecant function. So it could be written in this manner: 2 over e to the power of z minus e to the power of minus z. You're going to square that. We're doing this so that we would know what our goal is. So if we could arrive at the form of 4 over this form in the denominator without specifically expanding that, we would now arrive into an equivalent form, and we are now sure that our result is actually, our identity is really true. So our goal is this form here, this form, from our manipulation. And that is when we are going to start with this. So you have here the square of your cotangent, a hyperbolic function of a cotangent z minus 1 can be written as this form. So we're going to square this form minus 1. Okay? Since this form is already identified here, so you plug that in on our given form. So you will have here e to the power of z plus e to the power of minus z over e to the power of z minus e to the power of negative z. You're squaring that minus 1. Hopefully, from this, we could arrive at this form, which would give us the identity in itself. Let's try to manipulate this as we move forward. Allow me to use the power law of exponents, providing this to our first binomial expression for numerator and the denominator itself. So you will have the form, the square of e to the power of z plus e to the power of negative z. You're squaring that, and your denominator, e to the power of z minus e to the power of negative z, you're squaring that as well, minus 1. Now from this, actually, you would see a little bit of guarantee that your denominator is already there. Okay? So when we try to manipulate this, let's not expand the denominator because it's already part of our goal. We are going to expand only whatever can be found in our numerator. Hopefully we will reach 4 with this denominator, so that we are actually done with our process. So for this, we're going to combine the two terms. So we know that this is actually over 1. So by LCD, the same denominator as this one here, again you will have e to the power of z minus e to the power of negative z. You're going to square that. So the first term would still be this one, okay? But your second term will be minus this divided by 1 times that. Okay, that's how you apply, right, the LCD. So it would actually be the same denominator itself. Now I mentioned that we will no longer simplify the denominator, but for the numerator, we're going to simplify all of this. Again, hopefully we'll arrive at a value of 4. So the next part is applying the squaring of a binomial expressions, or you can even use here the difference of two squares if you're more advanced. because we have here difference of two squares, and you can actually look into that process and hopefully you will get 4. But for this and for the general process, allow me to expand the binomial expressions for our numerator. For our first term, it's the square of the first term plus twice the first term and the second term plus the square of your second term minus the entire group here. Notice that I'm placing a grouping symbol because all of this will be subtracted from, and then that means all of them will share negative sign. You have here the square of the first term minus twice e of the first term, the second term, plus the square of the second term, all over the same denominator, e to the power of z minus e to the power of negative z squared. Okay? Now, as for our numerator, you apply here the power law, multiplication law, power law, multiplication law, and you have here power law as well. Okay? So what will happen here is this. You have e to the power of 2z plus 2 e to the power of 0 because that's z minus z plus e to the power of minus 2z. Let me still come up with a grouping symbol for the second group. E to the power of 2z minus 2 e to the power of 0 plus e to the power of negative 2z, all over the same denominator, e to the power of z minus e to the power of minus z, the square of that binomial. Now, we know this to be 1, this 1 as well, and allow us to distribute down the negative sign so that we can now combine the first group and the second group. So you will have your e to the power of 2z plus 2, because again, e to the power of 0 is 1, plus e to the power of minus 2z. Now applying the distribution of negative sign, minus e to the power of 2z, the minus 2 becomes plus 2, the plus becomes minus e to the power of minus 2z, all over the same denominator, e to the power of z minus e to the power of minus z squared. Now, here comes the process. That and this are opposites, so basically when you add them, that's 0. This and this one here are also opposites, so basically again that's 0. What remains in our numerator is 2 plus 2 over the same denominator, e to the power of z minus e to the power of minus z squared, or we know that to be equal to 4. With this figure now, it's actually equivalent to this already. Okay? 4 over the square of the difference. 4 over the square of the difference. In short, this is actually 2 over e to the power of z minus e to the power of minus z. You're squaring that. I'm doing this because that's actually the target here, just by step, which yielded to this result. So basically, all of these notations yielded the square of cosecant, or the square of the hyperbolic function of cosecant z. And this shows our proof that from this one here, we arrived at this expression, which is actually the intended target of this video. This is how we prove the third Pythagorean identity. Not necessarily Pythagorean because it's minus, but basically we're trying to talk about the concept of Pythagorean. Again, it might not be Pythagorean because it's minus, but that concept is actually true when we're going to return here plus 1 the other way around as we move that there. Okay, so it still probably look like a Pythagorean, but anyway, this is the proof for this specific identity. Thank you very much for watching.